Hello, I'm Bill Wong with Electronic Design, and we're going to find out how we can make the developers' jobs much easier, especially in the automotive space. So can you tell us about your technology and how this works?
Yeah. So what we are doing here in this demonstration is a first that we are showing at the CES, and it's basically getting code that's running in a cloud-based simulation with the single push of a button to translate this to the embedded side of things, while keeping all the real-time properties, the sequencing, and everything perfect. So it means you can switch seamlessly between prototype development in the cloud and the embedded side with the push of a button. And that's a total new story, because on the embedded side we have a full series-proven ASIL-D capable safety platform for ADAS application. And we show this here by having a parking application that we run, and with the single push of a button get into a real embedded ECU running with the same timing behavior, everything picture perfect. And even if we put a high load on the embedded ECU, we can still keep the timing behavior of the critical applications and get a clear priority on that.
So what are some of the challenges that people had encountered before that you now have addressed?
So before it was like you did a simulation in the cloud, and that's basically, many of the simulations are a single big loop where you do everything. And on the embedded side, it's more real-time processing with different, let's say, loop times, more parallel, different SoCs and all this stuff. And so there was a difference in the timing behavior and the sequencing of things. And we fixed that. We learned it in the cloud what's the right sequencing, and we translate it to the embedded side and make this fully automated.
Let's stop the demo. On the right side, you will see the simulator, where the autonomous driving application is running. What we are going to show at the beginning as initial status is this autonomous driving running in the embedded ECU, and the situation in which in the ECU there are other applications that are trying to take CPU budget. So, and the autonomous driving will be stressed by these applications, and this is currently all the safety relevant conditions are not being taken care of yet. So what we will have, we will simulate this iCPU conditioned with CPU load, and we will start the simulation having the stress.
Okay.
So this on the demo control UI will now trigger the demo. What it will happen is that our autonomous driving applications are running within the automotive ECU, and on our simulator will simulate all scenario, all the cars models, all the cars behaviors of the models you can see right now in the video. And of course, in order to recreate and to test how the condition will happen if you don't take care of the interference that you could have by other applications. As you can see right now, the car is not able to run properly. It's gonna provoke a kind of an undeterministic scenario in which all the control nodes, the perception nodes of the autonomous driving will be affected by this. Okay, and this is of course not what we want. So what we could do is we can trigger our integration, automatic integration, and we can do it via a code push. We will trigger the integration and via this push of a button with commit changes. Now a new cloud campaign will be triggered. This cloud campaign is the one that is recreating all the integration. It will take a few seconds, and now we have a new cloud campaign. This is now taking the software and simulating the software in the cloud with the right temporal behavior. Of course, this is all happening like this is all triggering the new application stack. So it takes a few seconds to load everything. Now the all integration cycle has been triggered. We are in the pre-build phase. In the pre-build phase, we are simulating the application cycle, the application stack in the cloud. Now the scenario is being reloaded your application are running in the cloud with the expected behavior, how this will look like. How this has to look like on the embedded target. As you have seen before, on the embedded target before we had a baggy behavior, a non-deterministic behavior. Now we will run, of course, when you run in the cloud, you can use very high hardware resources because you can use like a very large amount of memory, you can use very fast CPU cores, so you can recreate the behavior that you would like to have if we don't have the bottleneck of the actual hardware that you're going to use at the end, right? So as you can see here in this simulation, the car is supposed to perform properly. When the other car intersects it, it will be able to perform the emergency braking function without any problem, and then still ensuring the emergency distance. But on the left side, you are seeing that the software that's currently on the ECU was failing. Now we put it to the cloud, and now it's working. So what we do now, we learn from this behavior. From this behavior, we run our analysis, and we want to bring this temporal behavior of the application back to the cloud. So we need to learn them on a statistics way to understand the processing time of the applications, the period of our applications, the model, the system model of the whole application, and what we call computation chains, which are how the applications trigger each other in order to guarantee the latency within the whole flow, within the whole sequence of applications that are triggered. Now the analysis has been complete, and we have a bunch of analysis related to how the x86 cloud architecture and how that will be translated to on the embedded target, on the ARM architecture. And we can see, just the auto has been triggered. We can see that this is going to be translated in a processing time. This is going to be translated in the statistical analysis of the processing time is, and how we translate to ARM and the period of the applications. And is also translated in the computation chains, all the sequence, all the nodes, how the nodes are triggering each other. Okay, and out of this we create now our new release. The release of the application stack is now integrated and is able to reproduce the right temporal behavior.
Okay.
And what we also have here, once we learn this new behavior, what we have is how these will fit in the CPU cores. So we can see here, for example, that each core will have their own application, this control output, which will have a proper execution time, and their period will be guaranteed by our platform. So doing so, there will be no problem of other applications that might conflict. Okay? And what happens now is that the over-the-air update is triggering a new simulation on the other side, with the expected behavior now on the embedded ECU.
Excellent. Well, thank you for telling us how you can make jobs of developers easier.